This is a digression from the topic of digital design. We will look a little bit in detail into the structure of an ELF file and how it executes on a CPU. The process by which an ELF file gets loaded into memory and executed is not absolutely essential to designing hardware, but can be useful to understand in some cases. In particular, it can help you to visualize where bottlenecks in software are and whether something could be fixed in software without necessarily creating custom hardware. In this video, we will look at the simulation trace corresponding to execution of a simple GPIO toggling program and correlate this with the actual machine instructions that are being executed. Note that it may be possible to do digital design with or without HLS without going through this and understanding the mechanisms in detail. On the other hand, building a good understanding of how a program actually gets executed in hardware is helpful in many situations and can help you to optimize and design your systems better. Please keep in mind that this video is not intended to be an explanation of how a general CPU works or even how exactly AXI-bus communication happens. So a lot of details are skipped and only a superficial explanation will be given. If you are interested in understanding it better, you will need to dig into the simulation traces yourself. We will first use the mb objdump command to dump out the ELF file into a readable format that includes information about addresses. Then monitor these instructions on a simulation waveform, and finally try and understand how exactly the GPIO write happens. The instructions that we will be going through are exactly the same as the previous example, which is the Hello World example. That is to say, the GPIO test program. The assumption is that you have already been able to build that project and execute it. If you have not done so, you would need to complete that before you can follow along with this video. Once the project is done, you need to go into the command line and change into the directory where the project executable file has been compiled. It would be inside a directory called SDK, project.sdk. And since the project itself was called GPIO test, or rather the software program was called GPIO test, there would be another directory called GPIO test. And finally, there would be a directory called debug, which contains the actual executable program. If you look in here, you will find that there are a number of different files. We are only concerned with the ELF file, which is what we want to actually understand. The command that we are going to use in order to disassemble this is something called the objdump or object dump file or object dump executable. In our case, we will give it the prefix mb hyphen, which stands for microblaze. So mb objdump minus d GPIO test.elf will dump out the object file. However, it will be a fairly large file. So what I'm going to do is redirect it using the pipe symbol into the program less. For those of you who are not familiar with Linux and Unix, please take some time to understand how these work. They are useful to just look at files. The pipe symbol in particular is used in order to take the output of one program and pass it into another. This has nothing whatever to do with digital design, but is generally helpful when you need to analyze and look at a number of text files. All right, so when we do this, we start to get information about the GPIO test.elf file. The first thing that we can see is the file format, which it says is ELF32 microblaze EL. Well, essentially it means that it's a 32-bit ELF file meant for the microblaze. After that, you see a number of small paragraphs which basically say disassembly of section something, in the first case vectors.reset, then you have disassembly of section vectors.sw exception, and so on. What has happened over here is a program that is compiled into an ELF file consists of many sections, and each of them has been disassembled or converted from the machine instructions back into assembly language over here. The first thing you can see is the very first section starts at address location number 0, which is where the CPU will start executing instructions from as soon as it is started. The leftmost column that you can see over here corresponds to addresses 0, 4, 8, etc. You will see that they are in steps of 4, which basically corresponds to 4 bytes, which is 32 bits, which is the size of an instruction. The very first section, the instructions at address 0, if you look at them, all that they do is it does a branch immediate to the location 50 hex, which is 80 decimal, right? So pretty much what is going to happen when the processor is reset is that the very first instruction it executes, or rather the second instruction after the immediate load, will be to jump to instruction location number 50 hex. If you go further down, you will see that 50 hex essentially corresponds to this label. There are a number of instructions out here. And if you go through it, it's not likely that you'll be able to interpret easily what exactly is happening. I am not sure of the details either. All of this is part of what is called the C runtime. These are instructions that are added on for every program that gets compiled using the C compiler in order to make it execute in a consistent fashion. This ELF file by itself has a lot of information, a lot of data which corresponds to the instructions. As far as we are concerned, the most important one is a section which comes way down. You will need to probably search for it. It is this section out here starting at address 69C, which is identified by the label main. This main corresponds to the actual instructions that are compiled for the program that you wrote. So let's switch back briefly to look at what the program was that we wrote in the first place. This was the program that we created to start with. You can see that you have the int main. This is exactly the same label which shows up in the disassembled data as well. What you'll notice over here is there's a declaration of an object followed by a GPIO initialize a call to a function and two further function calls over here, which are GPIO discrete write. If we go back to the obj dump code, you will see that after a few adds and store words and so on, there is a branch to an address which basically is marked as xGPIO initialize. Later on, there is another branch to an address which is marked as GPIO discrete write, and a third branch corresponding to the second GPIO discrete write. So in other words, the entire code that you wrote in int main and compiled got converted into just so many assembly language instructions. The important part, of course, is the actual GPIO initialize, discrete write, and so on are just branches. That's how a function call gets executed. All the adds and immediates and store words that you see before that are how the arguments to the functions are actually passed. You put things onto the stack, you fill up the registers with useful information, and then you do a branch to the appropriate location in order to execute the function. So we can also go a bit further down and look briefly at what the GPIO discrete write, for example, looks like. What you can see over here is the GPIO discrete write function is a fairly long function. It has a lot of instructions associated with it, right? And it's not entirely clear what they are, except that you can see a few labels over here that might help you to understand. For example, there is an XIL assert, there is XIL assert status, and so on. If we go back here and look at the xgpio.c file, you'll see that xgpio discrete write in fact has a few macros or function calls of its own. It calls an XIL assert void. There are 3 such statements. And finally, there is a GPIO write register, which in turn actually takes care of causing the write instruction to happen to the appropriate location. Okay, so now this hopefully tells you how to understand what an ELF file looks like. And if you go all the way back to the beginning of the ELF file, you can see that the very first instructions are loaded into location number 0. The start section is loaded into location number 50 hex. The main would be loaded in location number 69C, right? And so on, okay? Which means we can now take a step back, go back to our simulation waveform and try and understand how this translates into actually executing and writing out information on the GPIO signals. This is the simulation waveform that we had last time. What I have done is I have dragged in a few signals over here. The clock, reset, and GPIO were what we had already to start with. I have also gone a bit further into the actual microblaze system, the microblaze 0, which is on the left hand side over here. And I'm monitoring the instruction address, the actual instruction, the data address, and a couple of other signals that correspond to the AXI bus. Like I said, I'm not going to go into details of how each of these buses get their exact values. This is just a superficial view of what is happening. You are welcome to dig into it deeper if you are interested. All right, so let's go right to the beginning of execution, the very first time that we have over here. Time 0, I'm going to zoom all the way in over there. What you can see is right from time 0, the clock signal starts toggling every 10 nanoseconds. That is because we had mentioned that exactly this way in the system test bench, which we created over here. What we said was the clock starts with the value 1 and every 5 nanoseconds it toggles, which means that every 10 nanoseconds it completes one cycle. At time 0, the reset signal is given the value 0 and after 100 nanoseconds it is taken to 1 so that it becomes, since it is an active low reset, it is taken out of reset. So that's exactly what we see here as well. At time 100 nanoseconds, the reset signal becomes high, which means that the system has been taken out of reset. You will notice that there is some toggling activity going on the instruction and data address buses over here. Those are just some initial conditions that essentially corresponds to how the system actually starts up. It's not really possible to interpret this in detail without knowing exactly how the microblaze has been designed. So I'm not going to try and explain that. You will need to look further into the microblaze to see why there is this toggling of signals to start with. The next thing that you can notice is that for many clock cycles after that, there is actually no activity on the bus, right? You keep going through, you can slide to the side over here. The interesting thing is it is somewhere around 850 nanoseconds, that is 75 clock cycles after the start, that you actually start seeing consistent activity on the bus. Pay attention to the instruction address. It went from 0 to 4, which is the normal behavior that we expect from the program counter in a CPU. After that, it goes to 8. So in other words, it has first read instruction number 0, and you can in fact see what is happening over there. Instruction number 0, the data corresponding to that is available, well, right from the beginning, because that instruction address has been on the bus all along. After the instruction address changed to 4, one clock cycle later, we find that the instruction has changed to the second instruction in our list. If we go back to the beginning out here, we'll see that the very first instruction was B00, the second instruction was B8080050, which is exactly what we see here as well, right? The first instruction was B00 and the second instruction is B8080050. Going back to this code, we know that the second instruction is basically telling us to branch to location number 80. So ideally, the third instruction should just have been read from location number 80 or 50 hex. However, if you look at it, you find that the actual instruction is being read from location number 8. The reason is the microblaze is actually a 3-stage pipelined processor. What that means is that it takes a couple of clock cycles before it realizes that this is a branch instruction and is able to change to the correct location. In the meantime, the program counter has already gone ahead by 2 steps. It goes to 8 and then it goes to C. In the next clock cycle, it goes to 50 hex as we would have normally expected it to do. What happens to the 2 instructions that came from location 8 and C? they should just get ignored. The pipeline should get flushed and remove the effect. Of course, it is possible that there is also something called branch delay slots, and they might even be doing useful information. All that is beyond the scope of what we are looking at right now. In any case, what you can see is now the instruction addresses go along pretty much the way that you expect, 50, 54, etc. And the corresponding instructions also show up over here with a 1-cycle latency. If the instruction is a load or a store, you will find that there is also a data address which comes out here, which actually shows the information that is put onto the data address bus. Right? How exactly this is obtained is dependent on how the microblaze interprets its instructions. So we are not going to go into that detail right now. Now, I'm going to zoom out over here and get to the first part that really gets interesting, which is close to the first write to the AXI bus that we have. You can see that there's a lot of instructions that happen before that. In fact, if you look at it, the time is 3.6 microseconds, which basically corresponds to some 300 odd instructions that have passed since the beginning when the reset was removed. If we zoom into this place, what we will find is that somewhere out here, there is actually the instructions corresponding to writing to the data bus, and most importantly, the address location number 40000000, which, if you remember, is the address that was given to the starting address of the GPIO peripheral in the address map corresponding to this system. So in other words, there is some instruction out here that is actually telling the microblaze processor, write to this address location, 4 followed by 7 zeros. What data should be written? That would essentially correspond to the value 0, 1. And 2 clock cycles later, we find that the AXI valid signal write valid signal has gone up. Another 3 clock cycles after that is when the GPIO actually toggles its value. So what you can see over here is, even though we have given an AXI write instruction telling the GPIO to set the value of the pin to 1, it can be quite a few clock cycles before that actually gets reflected at the output. Once the GPIO has changed, 1 clock cycle later, it sends back a ready signal saying, okay, fine, I acknowledge that write, and I'm now ready for the next operation. And you'll see that the write valid also goes down as soon as it sees that the GPIO has acknowledged the write. Now, if we go further down here, what's actually happening in the software? If we go back to the GPIO test.c, the very next instruction as far as the software is concerned is, again, do a discrete write, but with the value 0. If I go back to the simulation waveform, you will find that there are a few clock cycles before the next instruction gets read. That's because the bus is essentially waiting for all the handshaking signals from the GPIO to get to settle down and to start working again. But after that, eventually it takes quite a lot of clock cycles and several instructions before we finally see that the data once again changes. This is the next AXI write that happens, and it causes the signal to toggle back to 0, the GPIO signal to toggle back to 0. The procedure is once again the same. The data address 0 has been put out there. The data write value is given as 0. That value gets updated over here. It actually causes the GPIO to change value. The GPIO acknowledges that it has received the write, and the write value then goes low corresponding to that. This repeats. If you zoom out, you can see that this basic process just is repeated again and again for an infinite number of times, essentially, because it's a while loop without any ending condition. The rest of the instructions would follow exactly the same pattern. So the purpose of this was to sort of go through and look into a little bit more detail into how an ELF file looks, how it gets loaded into memory, and how it gets executed on a CPU. You can As I said earlier, skip over a lot of this and you don't need to go into this level of detail in order to design hardware. But there can be many situations where understanding how exactly this works will allow you to design the hardware and the software in a better way that they work well with each other.